Well, hello, everyone, and welcome to PyData Global. We're excited to have you join us. Feel free to use the chat to connect to fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab on the bar on the right side, and we'll address them with the time we have left at the end of the session. Now, it is my absolute pleasure to introduce Saurabh. They'll be presenting optimizing AI ML workloads, resource management, and cost attribution. It's an exciting session that we've all been looking forward to. And if you'll join me in giving Saurabh a warm welcome, Saurabh, you can take the stage.
Awesome. Thank you, Arlitz. Hello, everyone. Good morning, good evening, wherever you are. Let's get through the hardest part of this, which is me figuring out how to share my screen. And hopefully you are able to see my screen as well. So I guess with that, let's get started. Hello, everyone. My name is Saurabh Garg, and I'm an engineer at Outer Bounds. And today I'm going to be talking about optimizing AI ML workloads, specifically from the angle of resource management and cost attribution. So Outer Bounds is basically building an end-to-end AI ML platform based on the open source project called Metaflow, which we will also talk about as we go through this talk. So what is on the agenda today? We are sort of going to talk a lot about cost and versus value of AI and how it threads through into some of the more common problems that data scientists and compute administrators deal with on a day-to-day basis, specifically from the perspective of resource management. And when I say resource management, it can either be HPC compute, or it can also be cloud compute that a lot of folks in the industry are gravitating towards. In some cases, we have also seen the same problems apply to locally owned data centers as well. But for the most part, it is agnostic of what type of compute we are talking about. So diving into what the problem of the day really is. So as with any new technology, even with AI, one of the biggest impediments is the very, very high cost of entry into building anything that is production ready and or meaningful to your customers. If you sort of think about the massive amounts of investments that are going into data centers and or infrastructure, it is kind of mind-boggling to think that industry leaders like Meta have decided to spend $600 billion on US infrastructure by 2028, or Amazon and Anthropic have decided, hey, we are going to spend about $50 billion in AI infrastructure, with Google pledging about $40 billion to invest in new data centers in Texas by 2027. Why are people really doing this? Most of this is because of this sense that AI can bring immense value, which like hitherto no unknown value to people, not only in the town square, but also help them be much more productive and essentially transform the industry as we know it to make people work better. An example, this is a slide that was generated by Nano Banana Pro. And I didn't really have to spend more than 5 seconds, basically punching in a prompt to an LLM, and here's my slide. If you were to take testimonials from industry leaders like Max Levchin, AI is going to be a great tool. It is a productivity enhancer. Or from folks from academia like Ms. Daniela Rus, who's the director of MIT CSIL. You can basically dig into every industry and you will find AI is changing the nature of work. However, there is a dilemma. The problem is, in order to build anything remotely useful, you need GPUs. And GPUs today are super, super, super expensive. In order to get around that problem, as I said earlier, folks have decided, I'm going to sort of trade large upfront compute capex for granular OpEx by basically renting the GPUs by the second by cloud providers, or any of these hyperscalers that we really know today, the AWSs of the world, the Azures of the world, and whatnot, the Oracles of the world, and GCPs. But while you have decided, okay, I'm going to rent out the GPUs, the second step sort of causes a huge burden or a huge issue for most people, because, okay, now that I know I want to rent GPUs, what GPUs do I need to rent? What is the compute that is right for me? What hardware is right for me? How much do I need? And if I rent out these GPUs, I have a team of, let's say, 13 people or 20 people. How do they use these particular GPUs? Like, can a single person use all the GPUs? Can multiple people use a fraction of the GPUs? How do I set these limits? To also, because at the end of the day, money is finite, even though cloud infra might be infinite. But what about the cost transparency? How do I know that these workloads that might be running on these niche pieces of hardware is actually producing value for me? How do I know that? If you were to sort of think about what are the GPUs that are actually available, I've taken an example of AWS and the types of GPUs, instance types that they allow you to rent out. There are about 40 plus GPU instance types that you can rent out from AWS today. And if you sort of think about it, a G2 8XL will allow you to harness about 5.2 teraflops of compute power, if you can use all the 4 GPU cards, and it costs you like $2.60. But a G4DN 8XL, which can allow you to harness 8.1 teraflops of compute power, has an on-demand cost of $2.17, and it's like 20% cheaper, and it has 1.5x more performance. But overall, across this entire spectrum, there is a 107 times price difference between the cheapest and the most expensive instance. Now, remember I said cloud infra is infinite? Yes, that is true. Or maybe it is not, because cloud is neither free nor infinite when it comes to GPUs. Like, there are only so many GPUs in the world. And eventually, yes, maybe there will be infinite number of GPUs, but today that isn't the case. So let's sort of dive into how we can solve all these problems. But before we do that, let's sort of take a small detour into an open source project called Metaflow, and how Metaflow will be able to help us answer these questions that we started off originally with. So what is Metaflow? So Metaflow is essentially a human-friendly Python library that was built to develop, deploy, and operate data science, AI, or ML applications. It is built on 6 pillars that go from modeling to data. Um, Metaflow, in its wisdom, sort of spans the entire gamut of problems that are faced not only by our data scientists, but also by compute administrators. Data scientists, for their own part, really care about modeling. And what I mean by that is they want to be able to use any and all Pythonic libraries that exist either within their own company, or they exist out in the wild, and they want to be able to do their work without having to consider, uh, you know, without having to make any considerations whether I want to use Conda or UV or Python for dependency management or whatnot. Once they use those libraries to write up their code, they want to be able to deploy these DAGs, which Metaflow allows you to write, to orchestrators like Argo or Batch, or any of your favorite orchestrators that you might or Airflow, or for that matter of fact. Now, let's say this orchestrator is executing your code, and in your code you want to version the artifact that you have sort of been generating and or storing. You don't want to be able to write any extra code in order to build any of that. So Metaflow bakes it in for you for free, so that you can track all your flows or experiments and artifacts automatically. Now, sort of coming to the other side of the house, which is more in the domain of a compute admin, which are the other 3 pillars, which are orchestration, compute, and data. Now, once the data scientist has written their their code, they want to be able to run it either locally or they want to be able to run it against cloud compute without having to do any sort of magic when it comes to setting up the connection between their local laptop and a cloud compute. Metaflow abstracts away all of that. So you can use the Metaflow orchestrator in order to run your flows locally while you're developing, and you can use it to access cloud compute once you are happy with what you've written. And it also integrates with with any and all modern data lakehouses like Databricks or Snowflakes of the world, or any of the databases or S3 clouds, object storage, what have you. So let's sort of see, we kind of use AI/ML workloads as a very loose term. So let's quickly sort of see what do these workloads really involve. So let's consider the jobs that a data scientist or a data engineer or folks who are working on Gen AI applications have to do on a day-to-day basis. These workloads can sort of span between interactive workloads to agentic applications, and how Metaflow really helps with that is Metaflow, as I said, allows you to write DAGs or directed acyclic graphs. And once you've written the DAG using very simple constructs like add step and and very simple constructs, then you can use Metaflow CLI to essentially run that code either on Kubernetes, or you can run it via Argo. And it is as simple as saying Python flow.py run with Kubernetes, and your DAG will get constructed into Kubernetes CRs and will get executed on the cloud. Now, the Kubernetes cluster itself could be deployed on your favorite cloud, whether it is GKE, Azure, AWS, or any of the neo clouds that you might have come across, which are like Nebius or CoreWeave. So in a sense, Metaflow is this one framework that allows you to do any and all of your AI/ML story. And it allows you to have very easy development cycles, which allow you to verify and debug locally and effortlessly productionize using dash with Kubernetes, whether it is on AWS, Azure, GCP, and on Nebius. So now that we have the problem set laid out and we know of at least one tool that allows us to very easily submit AI/ML workloads to the cloud, let's sort of see what would an ideal world look like where all your AI/ML workloads were running in a completely optimized manner. What are some of the considerations that you would have to think through? So, most data scientists might resonate. This image might resonate with them, where they sort of go to their compute admin and they're like, "Hey, we are going to run 15 training jobs this quarter, and we need like gazillion H100s." And in order for all of these workloads that the compute admin can already see coming in, if all of these workloads needed to be optimized, you have to think through, what are there definitely be predictable resource requirements for each of the workloads that is getting submitted into the compute cluster. Now, once the workload has been submitted, you do want to have maximum resource utilization for the workload that is running on the cluster. You want to minimize resource contention. That ideally, there should not be a situation where multiple workloads are asking for the same resources, leading to a situation where everyone is sort of queuing up behind one another because, hey, there's only so much compute left in the world. Failures are a story of life, and you don't want to end up in a scenario where you have to keep rerunning your workloads over and over again, and you jack up a whole pretty large bill because there were flaky failures. And you want to make sure that your workloads are running on an appropriate instance type. Going back to the example we saw with GPUs between G4 DN8 XL and G28 and G24 XL, you do want to be able to make sure that you're using the right instance type. So let's sort of deep dive into each of these and see how this can help you achieve a very optimal workload and optimal cluster that is executing a whole bunch of workloads. So, let's say there's a lot of data scientists and might also relate to this, where they go to the compute admin and they're like, hey, our AI/ML workload, like our workload that we submit regularly to the cluster, it took like 25 minutes yesterday, but today it took like 5 hours. And the moment the compute admin hears it, they are like, oh, are the node groups in my Kubernetes cluster not scaling up quickly? Like, do I not have enough quota, or are the nodes not sufficiently bin packed? Because maybe there's one workload that is sort of asking for an outsized amount of resources on the Kubernetes cluster, or the workloads, are they even being scheduled on the right instances? Maybe there are noisy neighbors because we never put any limits, which means that one workload can go ahead and can sort of cannibalize all the resources that are present on any given compute node. And like, are the workloads right sized? So these are all the questions that might go through a compute admin's mind whenever they hear questions like this. So let's sort of look at a couple of graphs that might help put this into more perspective. So I have a graph here where on the x-axis I have time, and on the y-axis I have cluster demand. So what cluster demand is essentially saying is, across all the workloads that are currently present in my Kubernetes cluster, or compute cluster, how much of CPU and how much of memory is being asked of the cluster, given the total amount of CPU and or memory that has possibly been attached to this particular cluster. And if you see, between around 10:45 to 11 a.m., the demand for the CPU has skyrocketed to 200%, and the memory demand has skyrocketed to 500%, which means you're pretty much, you're asking for a lot more amount of resources from the cluster than you have given it resources to the cluster, which means your compute and memory is basically maxed out. If you look at it from the other perspective, where you have workload demand versus time, you'll see, because there is such high demand on your cluster, the workloads sort of start queuing behind you. So if you can see here, around the same time, the number of workloads that were queued, which is the yellow line, skyrocketed from about 250 to about 380 or 390. Which means your conversations like, hey, why did my workload take 25 or 30 minutes, are going to become more frequent. And essentially, this also indicates that you need to add more compute to your particular cluster, so that the number of workloads can drain quickly enough, and you don't have to have conversations with data scientists. Now, in order to maximize the resource utilization, now assume that there's a node on which your workload gets scheduled, and in order to make sure that a single workload cannot use up all the CPU that has been that is allowed that is present on that particular node, you can put limits on the particular workload. So in this case, the workload is limited to use only 4 vCPUs, and as we can see, it has sort of ended up only taking up 2 vCPUs at peak. Which means that, and if you do this for every single workload, then no single task can take over all the vCPUs that are present on the node. Also, looking at it from a memory perspective, this is a really good example, because assume that you had not put limits on the memory request, then what you would end up seeing is this particular task, which is sort of on the trajectory to get killed, would have ended up taking, let's say, all 64 gigs of the node, thus causing noisy neighbor problems. So, but my task now has run out of memory, which in itself is not a good thing, but at least you've protected all the other tasks. Now, while just-in-time metrics are a good sense, you do want to sort of understand how the resource utilization is working over time. So in this graph, I have 2 graphs. On the left, I have CPUs, and on the right, I have the memory usage for the same workload. On the x-axis, on the left, I have time since the seconds, time in seconds since task start. And on the y-axis, I have how much how much quantity has been requested. So in the left side, as you can see, we requested 5 vCPUs, but we ended up using only 3.7, almost 4 vCPUs. But on the right-hand side, we requested about 75 gigs. And at peak, you sort of end up using 60 gigs, which means that you don't really need to optimize any. You might want to optimize a little bit on the vCPU side, but on the memory side, it is not so unoptimized that you really need to go in and optimize. Like premature optimization can also lead to issues because at any point in time, the data underneath that that your pipeline is processing could change, or and that could lead to failures that you don't really need. So optimization in itself is also a function of how much data you're processing, how much time you're spending processing that data, and what is the cost for failures and reruns. So those are some axes that you should sort of think about when you sort of talk about minimizing resource contention. So assume you had a node that advertised allocatable capacity of 4 vCPUs with 64 gigs of memory, and there is the pod on the right which is asking for those for all of those resources, and it has sort of come into a running phase. But now there are two other pods that are also asking for that for the same resource quantity. And the event that you do not have enough capacity available on your cluster, all these pods are going to start uh, queuing behind each other, asking for the same resource quantities. Couple of options to think about when we looked at the workload demand over time. It sort of immediately gives you a sense of, hey, there are a lot of workloads that are starting to queue up. So maybe depending on the workload priority and the SLAs, it might be a good idea to add more capacity to the cluster so that these workloads can go ahead and start executing. So let's sort of look at it from a node over time perspective. So as you can see, let's say between 2 p.m. and about 2:30 p.m., the C5 4x large C5 4x large node group suddenly had its certainly had the node requirements shoot up to about 100 nodes, which means that there's increased node demand in a time window, and it might indicate compute contention. Uh, you might also want to look at it from the perspective of the resource demand. So in this other graph, you might want to see, okay, how much there's a bunch of resources that are available, CPU, disk, memory, and or GPUs. What is the actual demand of the workloads of these resources that I have across any and all node groups? So I want to see, okay, memory is at about 1,000% of demand, 1,000% of all memory that is being allocatable. The demand is like super high. That means I need to at least add more capacity to this cluster so the demand can come down. Another sort of consideration to make is no single workload is the same, right? Like workloads differ by priority, by SLAs, by the costs that you are willing to spend on those workloads. So it is always a good idea to consider separating compute pools for rapid experimentation versus heavy lifting. And what I mean by that is, in a dev cluster, you might want to give capacity for, let's say, only M54 XLs, but in a prod cluster, you might want to make G548 XLs available that can scale up to, let's say, 20 nodes compared to a dev cluster where you might only want to give G52 XLs. And in an experimentation pool, you're sort of optimizing for spiky, low latency workloads, but a heavy lifting pool, you might want to optimize for steady state, high latency workloads. And then you can use an event queue to sort of let's say you have low latency workloads that are running in your experimentation pool. They might want to emit events, and that can sort of trigger downstream flows in the heavy lifting pool, which are of a higher SLA and which are near to a higher cost profile or a higher priority and whatnot. Now, failures, as I said, is a fact of life. So a lot of data scientists are like, hey, my workload has failed again. This is quite annoying. And let's say you're using Metaflow, which allows you to write DAGs. This is just a visual representation of that. And one of the steps in your DAG, let's say, is the process S3 files step, where it sort of keeps failing because there might be I/O timeouts, network timeouts. The file that you're trying to download is like so large that you're running out of disk space. There can be like n number of vectors that can cause the failure to happen. So Metaflow sort of also gives you mechanisms to deal with these. There are a couple of decorators that I would want to leave you with, which are the retry decorator and the checkpoint decorator. Now, what that means is the retry decorator essentially says, hey, if any step in your Metaflow DAG has failed, then you can restart that failed step using local compute or using the cloud. And uh, for spiky failures like network failures or IO failures, this is generally it will help you to get past these flaky failures pretty easily. But there are certain cases where you might want to use something more robust like checkpoint. So checkpoint is essentially, as the name might suggest, it allows you to save your state midway as you sort of go through a particular step. Let's say you might consider the case of GPUs. You might be at epoch 0 versus epoch 5, epoch 10, epoch 15. You might want to save your state at each of those epochs so that if that particular step failed eventually at epoch 20, then all the intermediary states have already been saved. And when you restart, you're not restarting at time t equal to epoch equal to 0, you're starting at epoch equal to 20. So it comes with a very straightforward API, which is current checkpoint is loaded and or save and latest checkpoint. Remember, we said at the beginning that choosing instance types is like one big part of the battle, because if instance type pricing can vary to 40x between the cheapest and the largest, sorry, 107x between cheapest and the largest, then what instance type is right for you? Because the optimal choice sort of depends on the workload itself. Like if you're unable to use the entire capacity or the entire compute power that a particular instance type is even affording you, then what's the point? So, for example, if you have a G52XL, which is allowing you to use all of your all the compute, which costs 1.2 like $1.21 an hour, do you really want to use a P38XL where you might use, let's say, a 20% of the actual capacity and the rest of the resources just go wasted? And the P38XL costs like $12.24 an hour. So choosing the appropriate instance type is sort of a big part of this puzzle as well. Uh, and finally, like there's always a trade-off between speed of experimentation or lowest infra cost. Now, a lot of times we hear from data scientists that, hey, I don't really care that uh, my workload takes like 5 minutes to start executing because it's executing at 1 in the morning. No one's really looking at it. But I do want stability. That I do want this workload to run end to end. But we also hear from data scientists like, hey, this workload needs to start executing within 5 seconds, within 2 seconds of the upstream event that has been triggered to initiate the execution. So whether the first option is you could optimize for cost by eagerly downscaling, and the second option is you could optimize for speed by lazy downscaling. So in the chart above, what you end up seeing is if you do eager downscaling, you end up with, let's say, a spend of 59 GPU hours in total, with let's say 160 minutes of human attention. But in option 2, you end up with 115 GPU hours because there's a lot of time. There's a window in which the GPUs are not really executing any workloads. Uh, and the fun part is the reduction in human time was only 20%, but the increase in compute cost was 95%. So that trade-off is something that depends on the case. Like there's no right or wrong answer to any of this, but it really depends on your use case. So assume we've done all of these things and we are now running in a super optimized manner. One of the core problems at our time of our time is, as I said, GPUs are expensive, and if you are spending, let's say, $1 million on cloud spend, you do want to be able to understand where is this money going and how much value is being produced by the investments that are being made in cloud spend. So you don't want to spend $1 million on projects that generate, let's say, only $100,000 in incremental revenue. You want to understand, like, where is the allocated money being spent, what products have the maximum ROI, and what are the granular tracking of cloud spend from team budgets. So leadership comes to you and they're like, hey, I want to understand, for all the flows that are executing, what how much of spend are we making. So they want to see whether it's a deep seek training flow or an event processor flow. Okay, I can see that the deep seek is taking a lot of money that we are spending day over day. Or I want to break this down via cloud spend by team, whether it's the data engineering folks or the data scientists or the data infrastructure guys, who's causing spend over the past 30 days or what have you. So in order to be able to answer these questions, it demands data. So the answer to that is monitor everything. So for effective cost attribution, let's say you were using Kubernetes as a choice of compute cluster, you could monitor every workload or node at different granular levels using, you could use things like kube state metrics, which give you metrics for node info, labels, annotations, and also for pod metrics like pod info, labels, and annotations. You could use advisor metrics that allow you to see how much CPU is being used or how much memory is being used. So if you sort of think about it from an architectural perspective, there are nodes on the right which are spitting out metrics for node information, and then you could have namespaces in which your specific workloads are executing, which are emitting metrics not only for CPU usage or memory usage, but also for native metrics like what are the labels on the pods, what are the annotations on the pods, and then all of that could get ingested via metric ingesters like Victoria metrics, and then you could potentially run Grafana queries in order to figure out how to do the cost attribution. While while this is just to get there's still one problem that remains, which is given the fact that multiple workloads do share compute, there is always the conversation around what percentage, how do you allocate the attribution, how do you attribute the cost of the node to specific workload, like what percentage goes where. That sort of still becomes a hairy problem to solve, but at least this sort of gives you a very high level overview of where you're spending the money and on what. So it allows you to contextualize spend commensurate with the value that you're producing. So that's about it from my talk. If you have any questions, happy to take them, or you can reach out to us on Slack, on slack.outofbounds.co, and there's a really big ML engineering community over there on the Metaflow Slack channel. But happy to take questions as well at this point.